Now we come to chapter 10 module 2. In module 1 of chapter 10 we have learned what is Z transform. In this module we shall find out the inverse Z transform of a function. That is, we shall have to find out the sequence Fn. To find the sequence Fn from its Z transform given by capital Fz equal to summation n equal to minus infinity to plus infinity Fn z to the power minus n, one has to find the inversion formula. Now the question is how to find the inversion formula. To answer this question, we consider two sequences Fn and Gn, which are defined by Fn equal to 1 for n greater than equal to 0 and 0 for n less than 0, and Gn is defined by Gn equal to 0 for n greater than equal to 0 and minus 1 for n less than 0. Then capital Fz, which is the Z transform of small fn and is given by summation n equal to minus infinity to plus infinity Fn z to the power minus n. Now Fn has been defined as 1 for n greater than equal to 0 and 0 for n less than 0. So this summation starts from n equal to 0 to infinity z to the power minus n, and which is equal to z by z minus 1 for mod z greater than 1. Similarly, Gz, which is the Z transform of Gn, which is equal to summation n equal to minus infinity to plus infinity Gn z to the power minus n, and with the definition of Gn, this can be written as minus summation n equal to minus infinity to minus 1 z to the power minus n, which is equal to minus summation n equal to 1 to infinity z to the power n. That is by some adjustment equal to minus z summation n equal to 0 to infinity z to the power n, and this summation is equal to minus z by 1 minus z, that is z by z minus 1 for mod z less than 1. This example shows that inverse Z transform of the function capital Fz equal to z by z minus 1 is not unique. That is, capital Fz is also z by z minus 1 and capital Gz is also z by z minus 1. So, in general, inverse Z transform is not unique unless the region of convergence is specified. Now, there are several methods by which inverse Z transform can be evaluated. That is, to find out Fn if capital Fz is given. In first method, we shall find out inverse Z transform by using power series. If capital Fz is given by its series, capital Fz equal to summation n equal to minus infinity to plus infinity a n z to the power minus n, where mod z lies between R1 and R2 as given by equation 1, then the inverse Z transform is unique and is given by Fn equal to an sequence. Consider the example 1. Here we are to find out inverse Z transform of capital Fz equal to z plus 3 divided by z minus 2 for mod z greater than 2. Here we write Fz as z by z minus 2 plus 3 by z minus 2, which can be written as 1 minus 2 by z to the power minus 1 plus 3 by z into 1 minus 2 by z to the power minus 1. which can be expanded and written in the summation form as summation n equal to 0 to infinity 2 by z to the power n plus 3 by z summation m equal to 0 to infinity 2 by z to the power m for mod z greater than 2, which is equal to summation n equal to 0 to infinity 2 to the power n z to the power minus n plus 3 by 2 summation n equal to 1 to infinity 2 to the power n z to the power minus n for mod z greater than 2. This can be adjusted to write as 1 plus 5 into summation n equal to 1 to infinity 2 to the power n minus 1 into z to the power minus n. So that we can write that capital Fz we know it is z transform of Fn, that is summation n equal to minus infinity to plus infinity Fn z to the power minus n. So, collecting the coefficient of z to the power minus n, we can see that f at 0 is equal to 1, that is for n equal to 0, Fn equal to 5 into 2 to the power n minus 1 for n greater than equal to 1 and Fn equal to 0 otherwise. So, this is one method of finding the inverse transform. Next method is to find inversion by complex integration. If capital Fz is regular in the region mod z greater than r, then its inverse transform can be obtained by using the formula Fn equal to 1 by twice pi I integral over gamma Fz z to the power n minus 1 dz as given by equation 2, where gamma is a closed contour surrounding the origin, is the domain of analyticity of capital Fz in the anticlockwise sense. We consider an example, example 2, find the inverse z transform of capital Fz equal to z plus 3 by z minus 2 for mod z greater than 2 by using complex integration. Here we see that R2 is infinity. So, we must have Fn equal to 0 for n negative. Now, from formula given by equation 2, we see that f at n equal to 0 is 1 by twice pi I integral gamma z plus 3 by z minus 2 into z to the power minus 1. Here we have substituted n equal to 0, and that is equal to residue at z equal to 0 and residue at z equal to 2, because the integrand has pole at z equal to 2 and z equal to 0, which can be calculated to be equal to 1. So, f0 is equal to 1. Now, we calculate f at n equal to 1. F at n equal to 1 from 2 can be seen to be equal to 1 by twice pi I integral over gamma z plus 3 by z minus 2 dz. Here the integrand has a pole at z equal to 2. So, this integral is equal to residue at z equal to 2, which can be calculated to be equal to 5. So, f1 equal to 5. Now, for n greater than 1, Fn is equal to 1 by twice pi I z plus 3 by z minus 2 z to the power n minus 1 dz, and this integration is equal to residue at z equal to 2, and which can be calculated to be equal to 2 to the power n minus 1 into 5. So, f0, f1 and fn are obtained by using complex integration for n greater than equal to 0, which is the inverse of capital Fz. In this module, so far we have learned how to find inverse Z transform by using power series of Fz and by using complex integration method. Now we shall learn how to find out inverse Z transform by other methods. Now we shall find out inverse Z transform by using Fourier series. If the domain of analyticity of capital Fz contains the unit circle mod z equal to 1 and if Fz is single valued on mod z equal to 1, then capital G theta, which is capital F e to the power I theta, is periodic function with period 2 pi, then we can expand it by Fourier series. Of course, G theta or F theta has to satisfy the conditions of expansion in Fourier series. The coefficient of the series are the inverse Z transform and they are given explicitly by small fn equal to 1 by 2 pi integral from minus pi to plus pi capital F e to the power I theta e to the power I n theta d theta, which is given by equation 3. To illustrate this, we consider example 3. Find inverse Z transform of capital Fz equal to 1 by 2z minus 1 for mod z less than half. So, using equation 3, now for solution we use this formula 3 to write Fn as 1 by 2 pi integral minus pi to plus pi 1 by 2 e to the power I theta minus 1 into e to the power I n theta d theta, and that is equal to 1 by 2 pi integral minus pi to plus pi 1 by 2 e to the power I theta 1 minus 1 by 2 e to the power I theta to the power minus 1 e to the power I n theta d theta. Expanding 1 minus 1 by 2 e to the power I theta minus 1, we write this as 1 by 2 pi summation m equal to 0 to infinity 1 by 2 m plus 1 integral minus pi to plus pi e to the power I n minus m minus 1 theta d theta. Let us put n equal to minus L where L is positive, then from this we get f of minus L equal to 1 by 2 pi summation m equal to 0 to infinity 1 by 2 m plus 1 integral minus pi to plus pi e to the power minus I L plus m plus 1 theta d theta. This integral can be evaluated to give 1 by 2 pi summation m equal to 0 to infinity 1 by 2 m plus 1 e to the power minus I L plus m plus 1 pi minus e to the power I L plus m plus 1 pi divided by minus I L plus m plus 1, and which is found to be equal to 0. Now let n equal to 0. So, from equation 3 we find f0 equal to 1 by 2 pi summation m equal to 0 to infinity 1 by 2 m plus 1 minus pi to plus pi integral e to the power minus I m plus 1 theta d theta. This we have obtained from here by using equation 3, and this integral can be evaluated and ultimately we get f0 equal to 0. Now we consider n positive. Then from here we first consider n equal to m plus 1, so that if we substitute n equal to m plus 1, then fn becomes equal to 2 to the power minus n, and for m not equal to n minus 1, this integral can be seen to vanish. Thus, inverse Z transform of 1 by 2 to the power Z minus 1 is equal to Fn, where Fn equal to 1 for n less than equal to 0 and equal to 2 to the power minus n for n positive. We can obtain this result by also by using power series expansion. Next we come to another method of finding inverse Z transform. This method is based on using partial fraction expansion. Let capital Fz be a rational function of the form capital Fz equal to Pz by Qz, where Pz has the expansion summation k equal to 0 to n akz to the power k, and Qz, the denominator, has the expansion k equal to 0 to m bk z to the power k, as given by equation 4. We consider first case where n is less than m. So, the denominator Qz can be factored, and let Qz, we can write it as c into z minus z1 to the power k1, z minus z2 to the power k1 up to z minus zm to the power km, where c is a constant and k1, k2, km are positive integers satisfying summation kj, j equal to 1 to m equal to capital M. Hence, we can write capital Fz as partial fraction in the form capital Fz equal to summation I equal to 1 to m, summation j equal to 1 to ki, a ij z minus zi to the power j, where aij equal to 1 by kj minus j factorial limit z tend to zi dki minus j dz ki minus j of z minus zj to the power ki capital Fz, as given by equation 6. The inverse Z transform of the fractional decomposition 5 in the region that is exterior to smallest circle containing all zeros of Qz can now be obtained by appropriate power series expansion of each term of the form z minus a to the power minus k. Next is case 2, where capital N is greater than or equal to capital M. In this case, capital Fz can be written as Fz equal to capital Hz plus Rz by Qz, where Rz has the degree less than or equal to capital M minus 1 and Hz is a polynomial of degree at most n minus m. The inverse Z transform of capital Hz, which is a polynomial of degree at most n minus m, can be obtained from Z inverse of small z to the power k, which is delta of n plus k, that is equal to 1 for n minus k and 0 otherwise, where k is 0 plus minus 1 plus minus 2 etc. And that of Pz by Qz can be obtained as in the case 1. Now we come to example 4. Find Z transform of capital Z equal to z to the power 4 plus 5 divided by z minus 1 whole square into z minus 2 for mod z greater than 2. We shall illustrate this method. For solution, we can write capital Fz as partial fractions as z plus 4 minus 1 by z minus 1 whole square minus 5 by z minus 1 plus 16 by z minus 2. And this can be adjusted to write as z plus 4 minus 1 by z square 1 minus 1 by z to the power minus 2 minus 5 by z into 1 minus 1 by z to the power minus 1 plus 16 by z into 1 minus 2 by z to the power minus 1. if we expand these terms binomially, then we get z plus 4 minus 1 by z square summation n equal to 0 to infinity minus 2n. This notation has already been defined into z to the power minus n minus 5 by z summation n equal to 0 to infinity z to the power minus n plus 16 by z summation n equal to 0 to infinity 2 by z to the power n for mod z greater than 2. This can be simplified to get finally z plus 4 minus summation n equal to 2 to infinity minus 2 n minus 2 z to the power minus n minus 5 summation n equal to 1 to infinity z to the power minus n plus 16 summation n equal to 1 to infinity 2 to the power n minus 1 into z to the power minus n. So, this is the expansion for capital Fz, and capital Fz is the z transform of small fn, which is defined as capital Fz equal to summation n equal to minus infinity to plus infinity fn z to the power minus n. So, if we consider f minus 1, that means z to the power minus n equal to minus 1, that is the coefficient of z, and that gives f minus 1 equal to 1. Coefficient of f, that is z to the power 0, that is f0, is given by f0 equal to 4, and f1 is given by the coefficient of z to the power minus 1, and that comes from these two terms, that is minus 5 plus 16, that is equal to 11, and fn is equal to minus 2n minus 2, this notation has been defined earlier, minus 5 plus 16 into 2 to the power n minus 1 for n greater than equal to 2. So, this gives the inverse of capital Fz, that is the discrete sequence Fn for various values of n. So, in this module we have learned how to evaluate inverse Z transform, and with this we conclude module 2 of chapter 10. So, in chapter 10 we have learned about the Z transform, and chapter 10 was the concluding chapter of this course on integral equation and integral transform.